be able to, I want to be able to get it going. So, hi, welcome. Hey, Lincoln, would you mind saying something official to introduce Karuna Labs? And
yeah, so Karuna Labs builds immersive virtual reality technology to treat chronic pain. And we bring in a lot of biometrics. We do EEG, GSR, and a lot of different other things. And basically what we do is we do these physical therapy exercises where you have these visual tricks where you see your body moving in ways that you can't move in real life. And we treat phantom limb pain, we treat complex regional pain syndrome, all types of complex chronic pain conditions where people are fearful of movement. But the reason why that's relevant to NeuroTech is, we're basically resolving these sensory motor incongruences at the level of the brain. So we use VR as a way to trick the mind into moving more and seeing yourself moving more in VR space. So happy to be host here. If anybody wants a tour of our facility, we have a little lab up there. If anybody wants to do a VR experience up there or toy around with some of the experimental stuff that we have going on, welcome to do so afterwards. I'm going to be upstairs, so thanks everybody.
What stage is your company at?
So we're venture backed. We're going through our Series A right now and going out to raise money again. But 10 people. Our seed round was led by Baseline Ventures, and we have Cleveland Clinic and VA as customers. So pretty early on, but.
How long do you think until you have pilot studies and government, fund reimbursement, medical reimbursement kind of thing?
Yeah, that's a good question. So for workers' comp, we are getting reimbursed. So that's one peer market we're looking at. And we completed 2 studies. We're in the middle of doing 2 more. One's in RCT with Penn Medicine. They showed great results. We got improvements across the board in terms of lowering pain catastrophizing, fear of movement, and pain scores went down. Medication also went down.
Somewhere on YouTube, there's a video of Ramachandran around 2000.
Big fan of Ramachandran, yeah.
Yeah, saying, one day we'll do this in VR, the phantom pain treatment.
Yeah,
It's going to cost $1 million now.
Yeah, so this is based off mirror therapy.
Yeah.
With mirror therapy, you have a person who has amputated a limb, and they feel and if you ask them, they'll say that they feel pain that's 11 out of, 11 out of 10. And it feels like there's a hand digging into their skin, and it's the most excruciating pain ever. And the way you resolve it is you stick that amputated limb into a mirror box, and you mirror from one side to another, and you see that visualization there. It resolves these sensory motor incongruences.
Yeah.
So we took that concept and those mechanisms, and we just apply that to other conditions.
All physical therapies.
Yeah.
That's interesting.
Yeah, so it's all about embodiment and predictive coding and doing all that stuff. So.
Question. So how do you trick the brain?
We do things like mirroring from one side to another. If you move a little, you can move a lot in VR. And it goes the other way too. So if you move a lot, you can move a little bit in VR. And it's all about embodiment. So you see your body in VR space. There's other cool things like you can move your arms with your feet with your arms. And over time that resolves a lot of pain.
Out of curiosity, and forgive me for asking too much, but some types of pain are indicative of causing more damage, and some you need to go through to heal. How do you know when you're doing your exercises therapy which is which for them?
Yeah, that's a good point. So we just do chronic pain, right? With acute pain, it's protective. You experience pain so you don't further injure yourself, right? You get a sprain, it's keeping you from further injuring yourself. With chronic pain, there's this maladaptive neuroplasticity, and what we're really trying to do is unlearn a lot of these pain behaviors
So you're basically only implementing what the physical therapist would have forced them to do anyway, or trying to get them to do, by helping them with VR to do it.
Yeah, that's the way to think about it. It's like you're going to go to physical therapy and do these exercises to give you more muscle tone, and you need that impetus to do it. And so we play these visual tricks on you so that you get to progressively overloading. So
Are you using any of the snow world techniques?
Yeah, Snow World, that's more distraction therapy.
It isn't. They've determined it has nothing to do with distraction. But that, if you give
I know what you mean. We have Snow World type experiences in it though, where it's like immersion and there's an effect with it. Like they did some naloxone, placebo stuff,
exactly,
right? Yeah, we're doing exactly the same thing. We have that plus
Plus other stuff.
virtual embodiment training. Yeah.
Do you see applications for performance enhancement or for athlete training?
Yeah, it's used a lot with, like we kind of backed into this where we're doing like post-surgical pain, and then as a result of that, there's just a lot of athletes that work with these orthopedic surgeons because they get injured on the job, right?
I've had two.
Yeah, and so there's a kicker at Stanford that started a company to do football simulations. So you put on a VR headset and you can see like patterns, right? So like they rehearse it in their head with VR, and it's amazing what it can do. It's
For the quarterback, right?
For the quarterback, yeah. Yeah, so they can do like these safety reads and stuff like that, and they get so many more mental reps through doing it through VR than they do in just practice. So workplace training is another thing that's really useful for it. Golf is now being used. All types of stuff. So I'll turn it over to Morgan to kick things off.
Sure. Thanks again, Lincoln. And excuse me for being distracted. I'm testing the live stream with Alex. and so, but let me get started. So thank you again. Welcome everyone. Bienvenue for any francophones who might be watching. And my name is Morgan. I am a neuroimager by training. So a neuroimager. So I do like MRI, fMRI, diffusion imaging, as well as other techniques for looking at both brain structure and function. So I don't want to get too bogged down into that. But welcome to the NeuroTechX first meeting of 2020, and this is going to review. So I'm going to give everyone an introduction to NeuroTechX, what we are, as well as then cover some neurotechnology news, some research, and then cover kind of what's going on in the Bay Area, which we're super lucky to have so many great institutions and companies working in this space right in our backyard, and then finish with just what our meetings will be about for the coming year. I can tell you some about the kind of the software and other kind of projects and events that NeuroTechX is going to be doing and sponsoring. So let me just tell you about NeuroTechX here, and we talked a little bit about the garage. There's a picture of the old garage in the Castro. So you can see Yannick over here. These are the BCI, open BCI, what do you call those, the Ultra Cortex? Yeah, the Ultra Cortexes. And that's Connor on the end there. Sorry if I can't recognize everybody. just pointing out Marion here, who co-founded the San Francisco chapter, and presented that the first, both the first San Francisco chapter meeting and the demo days back at Indiegogo.
Yeah.
And Neurables was one of the demos.
Yeah.
So it started in 2015 back in Montreal with three main three core concepts of, like, one, we're trying to develop a community of neurotechnologists, from everybody bringing their own skills, and perhaps their own goals in terms of as entrepreneurs as well as researchers, as well as just interested software developers and other people with skills to contribute. Education, we started NeuroTechX EDU, and this is both a kind of onboarding set of tutorials to get people up to speed together, and covering some of the open source projects that were kind of developed under the NeuroTechX name, although driving force behind this was Alexander Baruchon, who developed the MOAB and the Muse LSL, certainly the first generation of the software for the Muse that I brought here.
Is that a website? NeuroTech EDU?
NeuroTech EDU is a website.
Okay.
Yeah. And
With videos or art?
no, so we kind of crowd developed a set of tutorials. I mean, it's basically tutorials, and they're not a lot's happened. We've got new material for posting that I was actually leading, but it needs to be like that particular. A lot of that material hasn't been touched since 2018, and so anyway, I'll get a little bit more about what is coming with regards to that, and just the last pillar of NeuroTech is innovation, which means a lot of different things to people, but certainly there was a couple things I wanted to mention just about the early days. Also looking over some of the stuff Marion wrote for the first meetups. We definitely saw in particular things like EEG and virtual reality, eye tracking as very accessible technologies that people could work with themselves and utilize to their for their own goals and needs, and so going back and looking at some of the stuff from 4 or 5 years ago, it's been great to see some of the real success stories from that, and we'll be able to cover a few of those. So here are the chapters, with Montreal in its teal, and I've had the pleasure of at least visiting a lot of the sites, both in Canada and in Europe. I just got back from being in the UK for a couple of years, and certainly I know the chapters in Paris. London just changed hands, but we'll talk a little bit about that. But also Vancouver and Toronto, and of course Montreal. So NeuroTechX and Yannick get a lot of press, which really helps build our profile. But what's been great is not only the chapters building out, but the student clubs. At least in like 2017, 2018, it was great to see the student clubs, at least, wide participation across Canada. And we'll get to see a little bit of output. But this is something that we're definitely seeing a lot of growth in terms of providing, again, because of the kind of accessibility of this technology. These are great, kind of like both bioengineering as well as neuroscience, psychology projects that students can get involved with, and get something done in a semester or two. And we'll have a look at some of those. Like I said, the EDU platform, there's a newsletter, and most recently NeuroTechX Services, which is a separate, it's not something I'm involved with, but that is a commercial spin-off of NeuroTechX, where, we'll see a bit more. But I just wanted to show you, and hopefully this is going to work and also not crash my streaming. So this is just an example, one of the projects that one recently coming out of Montreal, and I'm gonna show you this video, or just a part of it.
We are McGill NeuroTech, and this is Milo, our brain-controlled wheelchair. The wheelchair is operated entirely by EEG signal, meaning it doesn't require the use of hands or limbs. It relies on imagined movement. To turn left, you imagine moving your left hand, and to turn right, you imagine moving your right hand. It has to be accurate, maneuverable, and easy to use, and we did this all using an EEG headset that cost less than $500. Let's start at the beginning. On February 24th, we assembled our team. We created a pipeline, starting with the brain and ending with the wheelchair itself. And this is how we did it.
I'm Danielle, and I'm leading the data collection team. We're the ones who are placing the electrodes on people's heads and actually measuring their brainwaves. And what was really interesting with this project is that we collected all the data for this project ourselves. So EEG is a wave-like, quite messy signal
that we measure non-invasively from the surface of the scalp. We decided to use an inexpensive consumer-grade PCI and passive lead electrodes. We put the electrodes on the sensory motor cortex, so C1 through C4, and attached them with a little bit of gel.
And so what we did is we presented participants with a cue, so indicating right or left or rest.
We did trials ranging between 5 to 20 seconds, runs lasted 5 minutes, and we did about 5 or 6 runs per subject for 15 subjects.
In order to troubleshoot, we wrote a protocol and compiled a list of known issues.
At the end of the day, we collected a motor.
Oh, my apologies. Well, I'm actually going to stop it there because the video goes on for quite a while, and at a certain point, there's music starts. But you got a sense of the kind of student projects, and what I definitely saw serving as a judge for 2017, 2018 was not only, these were great group projects, and people, by focusing on one of the particular tasks, they were able to build some really nice projects. Just related to the NeuroTechX EDU, the NeuroTech primer is going to be coming out. This will be a book that will be much more comprehensive than the online tutorials right now. And I'm going to be, I'll say a little bit about this in terms of, I think our online tutorials should be, as came out of a recent hackathon, Brain Hack at UCSF, if we were going to really do that, we should be focusing on more advanced software pipelines because the NeuroTech primer is going to be, again, a kind of like intro to neurotechnology.
Is that be available online, or is it more of like a
I mean, I believe it'll be available for purchase.
Okay.
Yeah. So, I mean, I can't say if it's a commercial, I don't know where the funds go. I mean, hopefully some of them go to, I know that some of the funds from NeuroTechX services definitely feed back to NeuroTechX, which is a registered nonprofit.
501c3?
It's registered in Canada, so we still need to get our US, and yeah, we can talk about what help we need. Sorry. Well, they keep on saying 5 minutes, and then it says another 5 minutes. So, sorry, Lincoln. So that is a work in progress, but it will be coming out this year. And
sign up for updates page.
Okay.
Are you,
takes you there.
Okay. And which page is this?
I just Googled NeuroTech Primer.
Okay.
NeuroTechX.com.
Yeah.
And has a sign up for updates button on the page. Which
I will let Luke know.
are you contributing editor?
Yeah.
No. I know they were looking for. Oh, please come on in. Oh, hi, Link. Yeah. So, hey, Lincoln be the person to talk to about chairs. Yeah. Sorry. So we're not too far in, but please, yeah. So, yes, I can't say much about the NeuroTech. I'm not responsible for that, but we will. Appreciate the heads up on some of the website things need to be updated, and so some of what this meetings or these meetings, different chapters is doing is trying to. Get us back so that there are people looking at the website. So NeuroTechX services, which is I'll just briefly. This is not for you. How many of you are unfamiliar with NeuroTechX? This will be your first. Okay. So this is just a nonprofit focused on. Developing a community of neurotechnologists, and I'll say more after 8. Yeah, and pizza's on its way. Just so you know. So NeuroTechX services, which is definitely more focused on do you have needs? Are you developing projects? And they're definitely trying to just help people in a consulting fashion. Again, I don't know much about that, but once we use Slack internally, and you can talk to Adam Zeffler on Slack about that, and the kind of consulting and recruiting. Certainly the job board is pretty impressive, or the job board has lots of opportunities if you're a developer looking for work and are interested in this kind of neurotech. And I definitely recommend that. So you can see some of the kind of jobs here, and I think we'll talk about BIOS later, but you can see, Konaku is definitely Berkeley. BIOS it says Cambridge there, but they're also hiring in Montreal. And this would be where this is the NeuroTechX's usual social media accounts, and you can get me at sf@neurotechx.com. And we also, our Twitter is NeuroTechx San Francisco, or NeuroTechSF, which will afterwards happy to make sure everybody's we've restarting the Twitter account for like it's been inactive for about 4 years, so we could use some likes. Anyway, so let me jump into some news that this is, these a lot of this slide deck came to me from Montreal, and so just the fact that, of course, they're looking at the Bay Area for a lot of development in sort of high-profile neurotech, and this is going back to 2017, but I don't know if how many of you were catching this in terms of the kinds of product announcements that certainly tech companies are known for. You might have thought, well, sure, this was announced at a developer conference, but we're not expecting anything to be happening in this this particular space. I don't know if I would have called it Kennedy's moon speech, but certainly this is what they wanted to. This is what they announced, and in terms of
Who's they?
at Facebook. So this was at F8 in 2017.
Hey, Morgan.
Yeah. Oh, yay. Okay. If people want to grab pizza, don't mind. But so yeah, Facebook, and I will jump into more details about this particular project in terms of the kind of invasive work that they're really building on later.
Their plan to do the 100 words per minute is with invasive tech?
Oh yeah. Or that's how it's actually being realized, and we'll talk about Ed Chang stuff.
That's
Yeah.
terrifying.
No. This isn't what they want to install in all of us. No.
Just their employees.
No. Well, what they do to their employees is apparently totally legal. But no. So again, like I walked a bit of a line in terms of looking at this slide deck, and a lot of this stuff certainly, because of NeuroTechX's focus, is somewhat consumer equipment, right? And I'm coming from research where it's certainly we looked at animal research predominantly in terms of what can you actually do,
Yeah.
and this will come up more with Neuralink. Neuralink is the more high profile. We're implanting something into your brain,
Right.
but this is why in 20 when they're talking about it, this is the problem with this particular slide, right? So 2017 is an announcement at F8, right? 2018 is an announcement at Asilomar, which is definitely a different group of people and is more non-invasive, or it's like Asilomar is definitely like a mix of invasive and non-invasive, but the invasive is all for people with like Lou Gehrig's and things like that, right?
Right.
So again, like these are the kind of cases where you want people are asking for invasive tech.
Either way would be impressive. It's
Sure.
been 3.5 years and
Sure.
they failed. How much?
No, they haven't failed. No.
100 words per minute?
Let me get to that. We're jumping ahead. We're jumping in.
How much did they promise to spend at that, at 2017? Just
Well, so there's a couple things. This is split across Facebook Reality Labs, Facebook Research, right, and then Zuckerberg Philanthropy, right? Because Chan Zuckerberg's have a lot of different things going on, and certainly the first stuff I saw was with Stanford Med in terms of invasive implants, and I didn't have much time to pull, but there's good YouTube videos of those. Anyway, 2019, the speech decoding Nature paper that they're talking about here is UCSF's work with Ed Chang. And again, long history of really wonderful neurosurgical work. And Ed's grids are, there's like 256 grid plus multiple strip grids, so he's got like 400 electrodes in the head. Plus, I think for these particular projects, they were also maybe testing smaller, denser grids. But anyway, the last thing, at least on this slide, is talking about control labs. I don't know if people are familiar with control labs. So this was super nice for NeuroTechX, just because Control Labs hired up Alexander Barachon, who again developed a lot of the NeuroTechX software projects, open source software projects, PyReman, Moab, Muse LSL, plus probably lots of contributions to MNE and other things. And yes, they were just this year bought up by Facebook. But in terms of hardware, this was essentially an EMG device, so capturing electrical activity of peripheral nerves in the hand. I guess plus gyros and things, but.
So in that case, that would be basically you think about moving your fingers to type, and it captures the impulses?
I mean, as
or you move a little bit?
as I understood it, so I think at UCSF we played with the Myos, and it was more about digitization. I mean, it was like, if you give someone equipment and you want to capture their arm movement, and like in a typical experimental psych study, you have them press keys on a keyboard, right? So say you want more degrees of freedom in that movement. That was what we were using. That's what postdocs were using in the lab with the Myos. Control Labs did seem to be like, at least when I think I caught some of their marketing videos, it seemed to be like a new way to not have a keyboard, but
Morgan,
yeah.
Are they only like targeting more like workplace improvements, or like geriatrics? Like everybody knows an old person that needs help doing something.
Sure. I mean, definitely, as I saw it, they were targeting more like consumer-facing stuff. And again, I'm sure like any startup, they were willing to pivot on a dime for whatever was working. But in terms, it would have been easy to sell it for other, for like aging populations. I'm trying to think what you'd need special in that. Nothing. I don't know much about them, but yeah. What I do know more about is in terms of Facebook Reality Labs, what they are developing is FNIRS, which is near infrared. So looking for functional near infrared changes, which if you're familiar with fMRI, how many people are familiar with fMRI? Yeah. Okay, that's good. 50%. That's like good. So FNIRS, you can do you're essentially capturing the same physiological contrast mechanism of blood oxygenation. It's got its own kind of noise, contrast noise problems. Definitely it's got its own acquisition problems. MRI, you're seeing in 3D nicely. Getting the sensors placed well for FNIRS is a real pain, but I love the pictures that Facebook's released in terms of like, it's nice. I mean, I've seen like 20 years of people making like weird 3D printed, headsets for FNIRS, and it's nice somebody with real money to come in and try and tackle that particular problem. So at least in the pictures I've seen, they've got lots of fiber coming off the head in nice movie movie production level sets.
So in that case, you're beaming in infrared lasers and
Yeah.
reading out.
Yeah, 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 and so it's you're trying. I mean, the problem you have. Oh, hey, yeah. Sorry, we got yeah. We might have to find chairs.
Yeah, those two are over there.
So. Yeah, sorry. F near. I mean, the problem you have is that there are other things that could change the absorption in terms of what you don't get, what signal you've lost. You can't just assume that it's because of the blood oxygenation. So again, what's super great about having Facebook, somebody with like Facebook's deep pockets, is that the software. It's perfect timing. So just talking about Facebook Reality Labs developing FNIRS. So one of the things that you need to do FNIRS right, especially as you try to capture more coverage, is real finite element models is the best way to capture 3D absorption. And so it's great to see. So Facebook Reality Labs is now looks like the premier sponsor of the FNIRS conference that's coming in October. Oh wow! Yeah, I was surprised. But Neuralink was certainly the bigger news, or it's. In true Musk fashion, he rolled out at nice multimedia events, and where they're describing implanting a very, very dense array into a very small part of tissue, small section of tissue. So a real difference between like what Ed Cheng is doing with the speech decoding. You're typically doing that in, or at least a lot of the research work is coming from neurosurgical patients that are getting treated for epilepsy or brain tumors, and you can put these arrays in, but these are very broad arrays across the brain, right? What Neuralink is describing is a very dense, multi-unit array placed in a very particular part of brain tissue. Now, there are lots of gaps missing from what they're going to do with that in their presentation.
Do you think they're easily upgradable? So, like, if you get the first generation, can you just like upgrade this, or you need to remove the entire thing and put in the second?
When they're doing it, I mean, so they're starting with animals now, right? So they put their human plans on hold and they've started with animals, right? And you can see from the people that they've hired that these are just a bunch of primate people. So so first generation isn't even here, right? I mean, I can't say. I mean, I don't have any internal knowledge, but everybody's increasing the density, but it's not clear. Again, what do you want to actually do, right? So, what they've said publicly is they're going to target, people who need to move limbs. Okay, so then maybe you don't need, like paradromic level, like 64,000 electrodes in a, millimeter cubic. Maybe you actually want a more distributed array of electrodes. I mean, it'll definitely, whatever first generation is, it'll be first generation for that particular purpose. Yeah, yeah.
What impact does the density have?
Well, so think of it as if you're familiar with kind of like the the body image that you have across the motor cortex, it's pretty distributed, So if a person really has no, again, it somewhat depends on the damage that the person has. Like, is it damage in cortex or is it damage in spinal cord? But you could use a distributed set of electrodes across, say, centimeters of cortex, right? If they needed to move a hand and a leg, those would have some distance. Whereas, what you saw, at least, and I don't think, there's so much to cover. We could pull up some of the images, but a lot of the companies are focused on how many electrodes can we fit in in microns, those are super useful for research purposes. Or I know what we would use them for research purposes. In terms of control, in terms of BCI for locked in, or not locked in, but Lou Gehrig's or something like that, where you've lost muscle control. I don't know if that's necessarily what you'd want to implant. Does that answer? Go ahead.
Well, we've talked a few times about how inhomogeneous the brain structure is. You're talking about such high densities per micron. You're talking cell by cell level. How do you decide where to implant?
So again, there were a lot of details lacking, and we'll talk about some of the specific applications. So when they were talking about if somebody's talking about memory augmentation, then I can guess where they're going to implant something, right? When somebody when the Strange Lab, because his name is Brian Strange, when the Strange Lab in Madrid proposed deep brain stimulation in schizophrenia, I was like, oh, that's awesome, but where? What's your target? And it wasn't clear what you'd actually go for. Whereas Parkinson's, exactly the cell types that are, dying and that you want to the activity that you want to replace. Again, they're talking about dealing with, motor control. And certainly the people that they've hired, like Flip Sabies, are experts in, primate motor control, and the kinds of arrays that you've seen in terms of getting a monkey to control a robot arm, is what I would imagine they would do, right? But in their presentations, they're talking about sorts of enhancement to the human condition kind of thing. It's a little bit more gray. I should keep going here. Right. So now again, I'm not responsible for these slides, all of these slides, but so not to harp on people who don't hit targets when they're trying to do really hard stuff. But Colonel was very high profile, another PayPal billionaire, I don't know, is that a thing? And I believe, or it's a different payment system. That's right. Thank you. And certainly I was catching his talks. He talked at Viva Tech back in Paris, 2016 or something. And I know that they were down as well, that didn't come out. They've pivoted to some other direction. I think it's focused on acquisition hardware. But it was originally, these implants to improve cognition, and I think you'll see a little later in terms of the kind of DARPA work that they were probably targeting, and these were going to be probably hippocampal implants that.
What is acquisition hardware?
Sensors you put in, dense arrays like paradromics in terms of. being able to record multiple electrophys channels. That's again, I don't know any of these people.
Is Kernel focused on non-invasive?
No, they were invasive. They were
Okay.
invasive. Yeah. And yeah, and I'm pretty sure that their hardware is still focused invasively. Yeah.
Okay.
Open water was the famous non-invasive in terms of, this is a woman whose background was in holography and some of the other, awesome physics involved in modern computer screens in terms of quantum dot stuff and things like that. We haven't, nobody's seen certainly any of these development kits, and it wasn't clear, it definitely seemed to be a description of something akin to not magnetoacoustic imaging, but it would be, I guess, photoacoustic imaging. So she was mixing some sort of optical with ultrasound. And again, like Berkeley certainly has published some theoretical papers on this kind of magnetoacoustic in terms of what you can get from these multi-physics approaches. I would love it if we really had this kind of resolution without, MRI systems. I mean, it does sound, it's hard to imagine how this would work without having the same kinds of sensor difficulties and confounds as near-infrared systems. Like getting a fiber to pass light the way you want at the interface is kind of hard. It's a hard I don't want to say non-technical problem, but it's if you're just focused on the imaging system, you forget about the problems that happen when you just, it's a hair, like hair is a big problem with FNIRS. And unfortunately, she doesn't publish anything to get a sense of what directions or what particular problems that technology would have. So I'm going to mention this just because so many of the initiatives, and this is pre-Obama Brain Initiative. Certainly, Flip Sabies is, I think, called the chief scientist at Neuralink, or certainly the person most involved in Neuralink's current efforts on motor control, was submitting DARPA grants for controlling, exoskeletons back in 2003, they're not quite what they were in terms of high risk. I'm pretty sure they're not supposed to have 90% of their projects fail anymore. that was their use. That was their old mission statement. But you can look to DARPA for. I mean, DARPA ends up being the project manager for a lot of projects. For those interested who have ventures that would meet DARPA's standards, there is an open. You can sign up to meet with program managers one-on-one in Chicago. You've got to sign up before Friday or by tomorrow. So if you're interested, I can get you you can sign up. That's just to talk to them about whether your project is going to be worth submitting.
Do they also support immigrants, or is it just Americans?
I think it depends. I mean, I think your company has to be U.S. owned. We can look into that. Yeah. So they are, again, they're the program manager on a bunch of related neurotech projects, and certainly, again, because of the Obama Brain Initiative, I think it was Cortera was definitely one that we'll talk about in anyway, let me go on to show you. So this is a good example. Again, I wouldn't read too much into this particular slide in terms of, there's a lot of money available and they need to keep their funding. So, again, these were projects that were actually in 2003 we were submitting for. So now they're saying 2030. But what I can say is that at Computational Neurosciences, the U.S. Army Research Labs had lots of posters. They're doing lots of great physics, like computational neuroscience physics, and there's the recent papers on big data approaches to ERP analysis. These were large multi-study projects that were together with Intheon. So they got a lot of press as like U.S. Army studies, brainwaves. Tim Mullen and Christian Cote were probably the really responsible for a lot of this work at their startup Intheon, together with UT Austin. And they've actually made code contributions to Genesis, which is a very old school C++ comp neuro package, which you can find in NeuroFedora, which we'll talk about later. So Therapeutics, this is one of the spin-offs from this DARPA RAM project, or Restoring Active Memory. And this was a nice one. This was on rat studies. And what's great about RAM is that they've released all their data. And there's also a Python package called PTSA, I think, that you can use for, it's ready to read that data and do some pipeline stuff. Anyway, the idea here was an implant in the hippocampus that detects when you are struggling to remember something, and it gives you, it's a closed loop system that then gives you a zap in the right place. Yeah, and I'm going to leave it as that vague because that's kind of what they were doing. But this is great stuff from this is the Computational Memory Lab at UPenn. So Michael Gannon and Dan Rizzuto, and I think they're both in principals at NeoTherapeutics. Lots of great papers, and like I said, these were, this was, I've got the website if you're interested, and it's certainly one of the things that we had talked about in terms of on Slack at NeuroTech, using that particular project as a great example of, because you've got this animal data, it's pretty rare, for people to be sharing that. So it's a great learning project there. Here's some of the other technologies that you might prefer to use. One of the things that they don't talk about when you're doing these kind of like Neuralink. One of what sells me on what Elon Musk is doing with Neuralink is really that I feel like he probably knows what he's doing in terms of robotics. And so, in some ways you could say that he's very focused on trying to develop medical robots to do the kind of surgical work that it takes UCSF people like 12 hours to do now, and they're going to try and do it in like half an hour, and I feel like that's very much the kind of, with his experience in other robotic fields, like that's something, he probably knows how to do. what you don't talk about is that like one of the real difficulties, one of the reasons why you want to make them small is certainly that when you're inserting this deep into the brain, that how much damage are you doing along the way, right? So this is I mean, one of the things that you know, when brain surgery stopped killing you back in the 1920s, so it went from killing you 80% of the time 1910 to killing you 20% of the time by 1920, right? So that was when they figured out how to do brain surgery without basically bleeding to death. But by the 40s, what they were really focused on was like, how do we do brain surgery and not do more damage to you than what we're trying to fix, you know, especially if it's deep. And because, you know, MRI gives you a great view of what's going on there, but eventually you've got to, you know, fit some sort of device into there. And so in terms of tumors and things like that, there's lots of things that people come up with in terms of like, how do I destroy a tumor, you know, with some sort of like needle and things like that. But with epilepsy, it's harder. And that's why they do all this language mapping. And, you know, it's like, we want to do this surgery, we want to help you and do, you know, whatever temporal lobe resection, but we also don't want to make it so that you can never talk again, you know. And anyway, so one of why these stentrodes get proposed is, so, sorry, your name again? Alan. So one of the, actually, this might.
Some conditions affecting the nerve cells in the body can result in disability. Spinal cord injury, stroke, limb amputation, and motor neuron disease or ALS may all cause paralysis, or even loss of the ability to speak. The Stentrode is a neural interface designed to overcome paralysis by creating a digital bypass from brain to assistive device. An investigational device, the Stentrode is inserted via a catheter into the jugular vein and manoeuvred into the brain without the need for open brain surgery. The sensors are built onto a self-expanding stent that engages into the wall of the vein and which is designed to maintain blood flow. Over time, cells may gradually grow over the sensors and incorporate them into the tissue. The sensors are placed immediately adjacent to the control center in the brain, known as the motor cortex. The patient may be paralyzed, but their motor control center can still be activated simply by thinking. The system is designed to transmit these brain signals out of the brain, out of the vein, and into a unit implanted under the skin in the chest. This unit is programmed to pick up brain signals continuously, and when connected to an external receiver, may send them to a computer. The command center in the brain is now directly connected to software, and the patient would attempt to train their brain for direct operating system control by thinking. Direct brain control of a mouse, a keyboard, exoskeletons, and even vehicles may become possible. Technology to restore independence. Synchron's neural interface technology, enabling people.
That's awesome. So I hope that explains like why they would go this way, right? Is that like, well, that's awesome. You don't have to cut open the skull. You don't have to. I mean, this is going for you know. So, and the other thing is that like it's quite big, right? It's over this distributed area. Part of that is that like this is a little bit more like the kinds of grids that they would insert when they're doing neurosurgery is doing like epilepsy brain mapping, and I think part of it is like by having this like wide array, they're trying to detect, you know, a wide swath of motor cortex.
So instead of opening the skull and doing lightweight surgeries to determine foci, they wouldn't take it out. They just put it in and leave it.
Yeah. I mean, essentially,
You can cut the wire. I mean, if you really want to get rid of it.
Yeah, but
that doesn't get rid of it. It's still in your.
Yeah.
Why not drill a small hole and put it, you know, above the dura beneath the skull? Out of curiosity.
Well, so I mean, that's really what Neuralink's trying to do, right? I mean, they want to, you know, enter here and then the different.
Catheter up and-
Well, no, because I mean you really can't do that. I mean they're going for imagine like inserting this filament, right? And so again as you know with publicly available information, it seemed to be like how can we get this filament to cause as little damage as possible and get as far as possible.
Right.
But they're definitely trying to get into tissue. You know, I mean, anyway, without you know, kind of analyzing their different business strategies, but you could definitely see the benefit in terms of this would avoid some, you know, not only the traditional surgery, but would also preclude any kind of collateral brain damage from the surgery.
You make damage to arteries.
Yeah. Again, I'm assuming everything's working. Yeah.
I mean, if you're paralyzed, you know, you don't care, right?
Right. I mean, yeah.
The video you showed, do you have any idea if they can go to arteries that are going down, deeper down, deeper layers than just the
I mean, you know, cardiovascular people could, or you know, they'll be able to tell you what they can get, because I mean this is similar to what investigational radiology people do. You know, I mean that's why I also feel like this is I like this concept because a lot of tech is focused on putting things into your you know circulatory system. So it seems like they would have a lot of stuff to build on. And then it really comes down to, and we'll see this a little bit.
So it's like
in
a stent with
yeah. And I haven't kept up on them in terms of, I mean, I remember them from a couple of years ago, but I don't know if they're, how forward they're going, but you know, what it really comes down to, so this is neural dust, which again gets a lot of press. But what I wanted to do by bringing it up was talk about certainly what you see with the Stentrode is that you start to really care about your material sciences because for these things you're talking about, I mean, what Neuralink talks about as well, but it's getting more and more important to think about what are the long-term consequences of having these systems in your body. So these are, and this is from this is over in Berkeley, and I think the idea is that these can also be ultrasound powered, I believe. Anyway,
what are they sensing?
Well, they're, I mean, brain activity, or you know, this is yeah. So, oh yeah, they are they're ultrasound powered. I posted, you know, again, like hopefully, if you're interested in more, you know, join the NeuroTechX Slack. Certainly, Jose Carmena's group. I mean, so this is 2013. I mean, he's got a new implant paper just this month, and again, this is all, you know, currently rat work, but I would look at that. Sorry, I'm behind on the slides here. Did everybody get food? Does everybody? Okay.
What's that?
No. Thank you. So these are visual prostheses, or you know, retinal prostheses. Different ideas here. So one, can you make an artificial eye, right? And then again, like I was saying, you have this problem of you need to know what the damage is in that person, right? So sometimes the damage is in the eye, sometimes it's in the connections to the eye. So actually, you know, providing an artificial eye isn't what you're what the person needs. So different technologies here.
Imagine you're completely blind, but your brain and visual cortex work fine. The ability to perceive and decipher images is intact, if only there was a way to capture and transmit those images directly to your brain. That's where the Orion Visual Cortical Prosthesis System comes in. It's a working artificial vision prototype being tested right now in 6 blind individuals who are helping researchers develop a new kind of machine-assisted vision.
So this is a prototype of the Orion system. Here we have the camera, the video camera that captures the scene in front of the patient. The signal goes down this cable to the video processing unit, also called the VPU, where the patient can adjust some of the parameters of what they're seeing. Things like contrast, brightness, and perhaps zoom. The image gets processed here and then is sent back up the cable over to the transmitting antenna right here. So this antenna transmits the signal to the implant inside the head. Not only does it transmit data, but it also transmits power. So the implant doesn't need to have a battery. So the signal from the glasses is received by this coil here, this antenna, and then it goes to the hermetic package here. This is where the electronics are that decode that signal and then provide the stimulation pulses that go down this cable to the electrode array. The electrode array is implanted on the visual cortex right there between the 2 halves of the brain.
To learn how the Orion implant gets inside a person's head, I visited UCLA.
So all the references and videos we will make available. I'm going to cut it off there. I think you get a sense of what the technology is. These are, this is not a move here. And of course, digital therapeutics. This is certainly big. Our local institutions. Adam Ghazali at UCSF, I believe, is the scientific advisor for Achille down there, and I'm going to talk a little bit about them at the end in terms of their recent studies on ADHD. But you know, because of tech's focus on exploiting the information in your digital footprint, you know, it's been you know, super attractive to a lot of companies, including of course Google's own efforts in health and mental health. So certainly for psychiatric applications, a lot of people have focused on, you know, what can we learn from your cell phone and from your social media, and a lot of that has to do with that we don't actually understand what mental illness is physiologically. So as one who focuses on physiological imaging of mental illness, but these are also things that get used. I mean, certainly another thing that comes out of Adam Ghazali's lab at Neuroscape was NeuroRacer, and you know, there are great ways to use games to, you know, study cognition and to study issues that people are having. You know, whether that's healthy aging, whether that's, you know, young adults and attention issues. There are lots of opportunities, and I'm sorry, Alex isn't here to talk a little bit about his company. Alex is also an old SF chapter garage alumni. But following what Lincoln had said in terms of Karuna Labs, they have this kind of Lucid Labs interface. I believe that's correct. Lucid, yeah. I mean, so in terms of adding some of these technologies to VR headsets, there are a number of existing companies. We've looked at a lot of the wireless EEG systems, dry electrode systems. I've never had the pleasure of using Neurable. Lincoln can tell you more about Lucid. There's certainly with Lucid, in terms of focusing on frontal, anywhere that there's not hair is going to be easier, and you'll see a lot of FNIR systems focus on the forehead for that same reason. And next mine was a recent one that announced at CES, and your visual areas, your primary visual cortex is right back here, as they talked about with the artificial eye kit. That I believe this is a traditional EEG device. So I'm seeing in the notes it says 8 dry electrodes, so I will believe them. I was hoping to get details from NeuroTechX Paris. Certainly the founder of this company is an experienced neuroimager. These hearable devices, interesting ideas of integrating EEG channels into headset, both earplugs as well as over-the-ear devices. Again, I can't say too much about them. These are more of the sleep kind of devices. EEG has traditionally been the technology you use to sleep score, to determine your stages of sleep. So the kind of predominant frequencies that you see in the brain activity can tell you what sleep stages you're in, and so together with movement data from say like Philips, they can tell you about how well you're sleeping, and of course the amount of REM sleep is super important. If you're not getting REM sleep, there are a number of problems that can happen.
So the dream is just EEG sleep tracking, sleep stage tracking.
I'm going to say yeah, they're adding it adds something beyond just behavior, so in terms of like, you can get these sleep pads that'll tell you how much you're moving, right? Or my watch. Yeah. Those will tell you something, but your sleep stages, I could imagine it, I'm just guessing here, right? But I could imagine it where it's like, if you're having breathing problems that's causing problems at particular stages of sleep, that you could get, this would be complementary information.
It's foolish not to collect dream stuff, though. Like, they should be.
Yeah, so REM is super interesting in that, like, if you don't get that REM sleep for one night, then the next night you will cycle more to make it up, right? And if you never are able to make it up, like, you can definitely have. Well, not
6 years and 6 years, 57 million. Are they selling anything? Price point? Anything?
Again, I'm willing to read the slides. I can't say I know all of them.
News is they've got a new headband that's like cloth and not like the plastic.
Gotcha. So I'm much lighter in the consumer space. I know. Yeah. I'm more interested in what Philips Neuro So Philip, we'll hopefully get there.
There it is.
So these are, oh, yeah, okay. So again, and I brought, for those who haven't seen one before, this is just a 2016 Muse, but this is the Muse device that works with NeuroTechX's Muse LSL EEG notebooks. And this gives you, it's just a super easy way, because especially it's focused on the forehead, give you 4 channels, and you can just be, get going with whatever you're interested in focusing your project on.
So how does that go in here? If you put it,
yeah, do you want to,
Like
we're going to have a demonstration.
These 2 go behind the ears. Yeah. I won't fully demonstrate because I've just had pizza.
Okay, no problem.
This goes across the forehead. These go behind the ears. Those are conductors. The rubbery things are also conductors.
So
that one looks like there's like 2 straps. The one from 2020. Or is it?
I think you're just seeing two
front and back.
yeah, front and back.
Oh, okay.
Yeah, two separate devices. I mean, two.
That was one device.
Yeah. And just covering the consumer devices, in this case, TACS, alternating current and DC direct current devices. These are injecting electricity into your head at low levels, and they are, I mean, again, UCSF, Adam Ghazali's lab has focused on some of the research applications of this. Neuromodulation, that was just October up in Napa, was a great conference to go to in terms of what's accepted as working with these devices and what is still a lot of unknowns. And it's still, I mean, from a physics modeling perspective, it's really interesting that if you increase the electrical dosage, as they call it, that you get nonlinear effects in the neural activity. So anyway, Hum is here. It was Australian based. Is now moved to Berkeley as part of their Skydeck fund. And I don't know Playdor, but I'm sure they're great.
What was the name of the Stanford one that blew up, like neurosomething, neurosity? There was Stanford,
Well,
a bunch of Stanford students created a company like 6-7 years ago, released a device and it failed. I don't know what the post-mortem was.
Well, that wasn't Neurosity. So Neurosity is a separate device. I think we'll have a slide from them. That's definitely more BCI. This is, but TDCS. I mean, lots of people are doing it. I mean, I would love one of these slides to point out NeuroTechx. So certainly NeuroTechx is what Adam picked up. Adam Ghazali's lab picked up early on, probably like 2015, and that was doing 32-channel EEG, wireless EEG plus TACS plus TES. Let's call it TES. I think they've been really successful. I mean, a lot of people were looking for headsets they could give people to take home, and I still wouldn't call those like super effective dry electrode systems. I think they were still wetting them. So somebody's not going to wet their own electrodes. Like if you give them these kind of devices, you could imagine sending people home, and
These were
certainly they're talking.
selling eyeglasses, it was dry electrodes, and it was advertising all of these,
We'll find out. We'll find out.
Yeah.
Yep. So for those of you who maybe are interested in this kind of stuff, I've taken devices through FDA approval. There's guidance now for BCIs, and I just took EEG, so EEG's really safe. Once hardware engineering's done its electrical safety, like we don't have a lot that we need to do in terms of it's not a high risk device. Anyway, there is now guidance for this, as well as some other we'll cover in terms of, I believe, TMS later. Yeah, I mean, I'm just gonna leave this as like it's an important issue. I am not so worried about what Neuralink can do, or because I think they're very far away from product. But I look at the continued use of like lie detection systems by the U.S. government in terms of security clearances as just plain pseudoscience. I definitely have issues with what I would call neuroethics, but I think that it's somewhat backwards in terms of we apply pseudoscience to actual high risk classifications, security classifications, when we shouldn't. and there are lots of issues that will come up, I think, more in terms of what I think is probably going to be a bigger problem is, of course, the same kinds of things that we talk about in terms of AI bias. And when classification systems are trained on homogeneous populations, then applied to different populations, and then you get all sorts of problems. Like, you're only as good as your training data. So I think that neuroethics is definitely something to talk about, but that what we're really talking about is the same kinds of machine learning bias problems at root. Anyway, so again, I'm more focused on lie detection and the kind of tools that are used in both law enforcement and security, and lie detection systems are still being marketed beyond just lie detection tests that you go through for security clearance. Some are actually focused on information extraction, and happy to talk about that sometime. So, yeah, and what I thought was kind of missing, so in terms of Philips, I thought the more interesting Philips purchase was a company I used to work at, Electrical Geodesics, and I don't say that just because I worked there, but why did Philips buy them was, I think, to focus on epilepsy. And certainly, if you are interested in EEG for clinical applications of EEG, the only currently billable service is really epilepsy and to some degree sleep. But epilepsy is the mainstay, and there are really great data sets from the first was the Temple University Hospital corpus in terms of people are releasing thousands and thousands of clinical EEG recordings, and so we'll talk about that briefly in terms of open source projects under NeuroTechx. The only thing I put there was the MEG CPT codes are good to follow. So for those not familiar, MEG is magnetoencephalography, where you're using magnetic field sensors to detect to detect neuronal activity. And the reason I say that it's good to follow the insurance codes for MEG is that MEG is really expensive. So it used to be an MEG system would be like $1 million, whereas a clinical EEG system could be $5,000 or $6,000. So what was interesting was like what you could see the MEG manufacturers do in terms of getting billable codes for insurance purposes, which of course is what makes a business, or certainly a clinical neuroimaging or neuromonitoring business. So MEG manufacturers and what their what they're allowed to bill for are good good prospects for high density EEG, which can be a lot cheaper. And again, that's always been electrical geodesics is focused on high density EEG. And if you haven't seen some of their nets, these are the nets that use just small sponges and saline solution to apply 128 or 256 electrodes across the head.
How do they do with hair?
And then there's kind of like the plastic holder for the sponge is also designed to move the hair aside. Okay. You know, and I want to keep us on time. Sorry, but I could say more. Like in their case, I don't think it was hair that killed them. So the news, the 2020 news, and at least in terms of Philips, is that Philips Neuro is winding EGI down. And some people think that that's because even though they had this very quick application time, that changing clinical practice, disrupting clinical practice is not always a question of do you have the right technology, right? And yeah. So. Okay, so jumping into some research news, and I might jump through some of these. I don't think anybody's. I would just pitch one thing, that the Open Worm project is a really awesome project that also gets Google Summer of Code submissions. So if you're interested, certainly I love psychophysics and try to use psychophysics stimulations as a visual scientists, especially those at the Smith Kettlewell Eye Research Institute here in the city, like to use psychophysics stimulation, because then you're generating something, you know exactly where it's going to appear in the visual cortex, and you know something about, say, its frequency form that allows you to say things, allows you to improve your detection and say things physiologically at a low level. So yeah, I'm not sure, I feel like this should be in the back in the industry news. So this is FDA clearance for TMS. I can say more about that. This is not only for depression, but also for OCD. This has been, yeah. And I'm particularly interested where you use the TMS. I mean, basically, this is, generating a magnetic field and it's stimulating the brain, but in very, very broad fashion, very different than dense electrode multi-unit arrays. And but it's interesting because if you record the EEG after that stimulation, you can kind of say something about the mass action of neurons that might give you something that's detectable if you're like me looking for physiological biomarkers of mental illness, for instance, or certainly other physiological problems.
How do you feel about the reports that you could make a savant using that tech, like mass savants or weak savants? Like you would have temporary savantism using
TMS?
Well, deep magnetic stimulation using super powerful magnetic fields.
Do you have a link for me?
I can send you one.
Okay. I mean, I will have a look at it. No. Yeah. So this had come up in a recent neuroethics. When neurosurgery is stimulating your brain, they've got your skull open and they're doing stimulation and asking you about it. I do remember there's a difference. I remember this report of when they're doing it electrically, you feel like somebody's making your hand move. When they do it magnetically, you feel like you decided to move your hand. I would have to find that reference. Anyway, so this again seems like it should be near the Stentrode. This is injectable electrodes. Is basically what it sounds like. Are any of these video? So I'm gonna just move on. Dude, we really make zombie pigs. Well, yes. But I'm not sure that's really of interest here. The zombie pigs are certainly pigs and sheep are used for a lot of research, especially if you want to look at multi-organ things. Studying gut brain relations is something that typically is done in pigs.
That was mostly about like cryogenics.
I believe you in terms of restoration of blood circulation post-mortem. Yes, good. I would be interested to hear. I mean, I did a lot of magnetic resonance spectroscopy, and that used to be used in terms of determining particular, basically like neuronal death that's not structurally visible. And it would typically be used in cases of drowning. So very unfortunately common in Southern California to have kids fall into pools and they don't die, and so there's assessments made, and I've heard that there's been some improvements in terms of recovering drowning, oxygenation. I don't know if these would be relevant to the zombie pigs. So what I would put, this is just a quick, some quick notes without pretty pictures. But in terms of the cerebral organoids, this is like growing brains from stem cells. UCSD has been doing this for like 5 years. First cerebral organoid paper was 2012 in Vienna, but Mutri runs the stem cell program at UCSD and has been doing, I think, the best work on this. Bradley Wojtek, who did his grad school at Berkeley and then in Adam Ghazali's lab as a postdoc, did the EEG analysis so that these organoids start to develop brain rhythms, which is really remarkable. And to get them to past a certain age, though, what you might want to do, they lack vascularization. So what you can do to get them to grow to a later stage is to implant them into an animal. And it doesn't, not into the animal's brain, but just into some part of the animal to allow the animal's vasculature to take over. So that's something that's going on at UCSF and the stem cell group at Parnassus. And the organoids have, great applications in terms of, personalized medicine, glioblastoma. If you wanted to see how your particular tumor would respond, you would want to grow this faster. And so it's kind of interesting that one of the, so Allison actually was here to speak at the Exploratorium about his cerebral organoid stuff. And the organoids that they took to the space station when they were brought back, they hyper-accelerated in their age. So super interesting in a number, like one, why? And then two, that would actually be really useful, right? So it's like if you needed to understand how your brain tumor is going to respond to various treatments, and you want to grow yourself a brain, well, Alice's work, Dr. Moultrie's work, still requires like you grow it, right? And so if you want it to get old, like you might need to wait a year. Being able to turn on accelerate aging would actually be a wonderful technique for this kind of organoid work, and in general across other organs too, right? But interesting that his space station example was, it turns out to be a hyperaccelerant. So people at the Buck Institute must be interested in this. And I'm going to, I've never really enjoyed this characterization of thoughts transmitted to brain-brain interfaces. This is like BCI, creating a BCI binary threshold, then tying it to the internet, and then tying it to deciding whether a TMS is going to fire or not fire. It's like, anyway. In the interest of time, I will, if anybody's interested in references to these things, just let me know. Now, I think this is oops, sorry. Oh, Lord. So, now this is not, this isn't Ed Chang's work, but it is, these are the kind of grids that you'll see neurosurgery implant. And they are using deep learning in this case to recreate the speech. Oh, sorry. I feel like I've done something wrong here. Try that again.
The proof that you are seeking is available in books.
The proof that you are seeking is not available in books.
The proof that you are seeking is available in books. Shipbuilding is a most fascinating process.
Shipbuilding is a most fascinating process.
Shipbuilding is a most fascinating process.
Oh, well, okay. My apologies. That is also Ed Chang's work. So he might have done the grids, but I think it was a different deep learning group. Anyway, I think this was set up to also just show that that deep learning can be useful in this case. I think there's definitely something to be said about interpretable deep learning, but a different conversation in terms of deep learning applied in multiple health technology contexts. These are just some example papers that Eric Topol recommended. There's lots of good examples. These are research slides, so this is a little bit more of my interest. So I can describe this after for anybody interested in terms of large-scale fMRI analyses and the problems that come from them. This is definitely, it's an interesting paper, is really relevant to my graduate work. Apparently there was some ethical problems with this German neuroscientist. which is why we advocate for more open science and transparency on all fronts. And certainly the paper down the bottom, Jonathan Walpole is believe founded the BCI Society. Certainly generated a lot of the open data sets that we still use as benchmark data sets from BCI, even though they're at this point like 20 years old. And sorry to keep you so long. So the local news, I think we can probably skip. I was going to, happy to cover, research in different, both in radiology as well as EEG, but it kind of gets to one of the reasons that we were interested in NeuroTechX's mission of DIY brain reading is that a lot of the systems and equipment that we're certainly trained to use are super expensive and are parts of shared facilities. Eye tracking, EEG, and certainly some of the kind of the equipment that you see connected with virtual reality systems are all very consumer accessible in terms of costs and programmable in the sense that I still believe there's a lot of information in the EEG signal for one, in terms of physiological information in the EEG. So I gathered lots of research in the Bay Area. I've gone over about 40 minutes. I wanted to talk about just one in particular, which would be Amit Etkin's EEG guided depression treatment. Just because I think, because it's depression, because it's EEG guided, so it's this kind of super accessible. I haven't actually seen it in terms of what the channel count was, but this is where he's using your EEG to tell whether you will be a responder to a particular antidepressant. And so there's, I've posted in the Slack, so in the NeuroTechX Slack, in the research room, I posted both the paper and the Twitter commentary on the stats, because several biostatisticians chimed in immediately about some issues with what is being done, but I put it as a challenge to you to read that paper and then try and figure out what the biostatisticians are going to pick up on, because it was pretty it was pretty arcane.
You take the antidepressant and then you just get EEG readings and it guesses.
Well, it gets the EEG readings to decide whether you will be a responder.
Just that's like what the Amen Clinic does with SPECT scans.
We would love to know more about what Amen does with his SPECT scans. Okay. If he was,
How big was the population that you built the database that?
Yeah. So in this case, there's going to be, I think, some issues. They weren't bad numbers. I think they were like 300. Which for some of these studies is good. At the same time, neuroimaging has changed dramatically since I was a student in terms of everybody's working with thousands of subjects of data. This is this month.
When was the data collected?
Oh, probably in the last couple of years.
So I would feed it all into deep learning, and then the statisticians can't say anything.
Yeah, that's another recent paper, or certainly, can the statisticians figure this all out? And so why I would pick that particular paper to look at. One, I like it because it's trying to tackle mental health. I mean, it's a psychiatric application of this technology, right? And it's EEG, so it's not some super expensive machine that you need. I wish we got EEG from all our inpatients. And I will say one thing for Eamon is like, at least he gets neuroimaging on all incoming patients, right? Look forward to him releasing that data. So this is this is a great paper to look at, and it's a great paper to also catch the Twitter commentary from biostatisticians in terms of, it's hard stuff. It's hard stuff to pick out still. And I think it's going to be particularly hard because, I mean, it's still a weird thing, right? Like you're trying to find a subpopulation that respond to antidepressants, which could actually improve the use of antidepressants. But then there's still the follow-up question of, well, what about in 3 years? Like, are they still responding to this antidepressant with time? I mean, all the old issues with SSRIs might still be totally applicable. So there will be time to talk about all the wonderful, sorry. Get to 9. For anybody interested, there's a new movie coming out, I Am Human. Okay.
Brian Johnson, I think, his girlfriend.
Well, certainly, there's the animal researcher. I mean, there's some great people in it, some researchers in it. I saw it and said the babies on Netflix I saw, and they're using EGI nets. So anyway. And I've got some book recommendations, but I just wanted to get to. So what do we do at NeuroTechX? Like our events are not going to be like this every week. Although I'm happy to extend these slides out for a lot of material I didn't get to. But we are trying to build community, educate, and do workshops and get people familiar with analysis pipelines. I like to say that there's even if you're not focused on neurotechnology, that this is a really interesting way to learn data science. And certainly a lot of computational Python. We mostly use Python, which has lots of other uses. M&E Lab is so I'm making some suggestions for changing our EDU program. We've got a nicer GUI tool that you can use for looking at multi-channel EEG now and doing signal processing that is important for extracting features as well as making some potentially brain-computer interface kind of decisions or clinical decisions. There's some great some related tools in terms of do you have a new hardware device that needs acquisition software, M&E CPP. And then I'm also, I co-founded NeuroFedora. I've been a very happy member and user on this laptop of NeuroDebian. And we've got some tutorials that Ankur has put together for computational neurosciences in terms of playing with models of spiking neural networks and things like that have a variety of uses. So the Mozilla Science has been a great supporter of open source hardware. I very recommend MozFest, anybody who can make it to London. I was there in the UK, so it was easy. Didn't get to go this year. But at NeuroTechX Moscow is the free EEG32 project, which is a wonderful upgrade board from OpenBCI. It's a more expensive board, but Dimitri releases all his stuff, GPL, and it's actually what I'm recommending people who are interested in learning hardware. So our own Jean Rintoul, you might have caught OpenEIT. So this is a crowd supply project she put together, and she's got talks available. You can find on YouTube at DEF CON and Chaos Computing that were great examples of things that Nguyen and I worked on. Just 2D, she's got 2D hardware for doing. For OpenEIT, but super interested to link that up with Phoenix Python software for doing finite element models. And Mozilla Science Fellows have supported a lot of open hardware events. And if you want to get the references from me, and I've added to these slides, yes, please stay in touch on the social media platform of your choice. Although internally we mostly use Slack. And that will wrap it up. Thank you so much.